Hi guys, welcome to the video. My name is Chinmay and this video is going to be about some fundamentals about Rust. So I will be talking about how Rust is different from other languages and what does it do explicitly and why it is termed as difficult by many developers. So the topics that I would be going over are two. First is the most syntactically obvious, which is object-oriented principles, OOPS. And Rust does not allow creating objects or classes. So that's the first visible difference when you code in Rust. It does not have any OOPS. And the second difference is behavioral, and that difference is that Rust does not have a garbage collector. So you have to make sure as the developer that you do not have any memory leaks the way you code it. And let's go over into the code to explain this better. So uh, let's create cargo.toml, and there are some things which you need to have some prerequisites. For example, having cargo uh, installed and having Rust installed, but I'll mention the links in description so you can do that before going into this video. So I've created a workspace and I will be creating a new package. Let's name this mem because we will be going over the fundamentals of memory, which is related to why it does not have objects and why there's no garbage collector. So this is a package. You can see a new package has been created with its own main Rust file, and every Rust project has a main file. Every package has a main file. And how Rust works is needs to be compiled and to be converted into a binary, which you can just execute from any terminal. So this Rust is actually machine agnostic in a way. So let's jump into the code. What I mean by garbage collector, if you're not aware about it. So let's assume that you create a variable x and you create another variable y, and so what I've done is I have created two variables and I've printed only one of them. So what this means is I am defining a variable and probably I'm not using it after a while. So what happens is the memory which is allocated for this variable, that memory needs to be freed because it's not being used anymore. And so what a garbage collector does is it is a background mechanism to see how many variables are being referenced, and as soon as the reference count of those variables goes to 0, the memory is freed. So the reference counting is how garbage collector works in Python. Multiple different languages might have different ways of doing it, but that's what garbage collector does on a high level. So freeing memory which is not needed. But Rust does not have a garbage collector. What this means is we need to make sure that the code does not have any memory leaks. And why is that? Because the way memory is allocated and accessed is often through pointers. And let me show you let me show you more visually. So I have kind of a diagram here of a stack and heap. Stack are two different kinds of spaces, two different kinds of way we can allocate and deallocate memory. So generally in many languages we have pointers, and how pointers work is, let's say you have a variable which is of value 5, and the address of this is a. So you have a variable. So you have a variable stored at address a with the value of 5. Now you can have another variable which is actually a pointer to x, and how that works is the value of x is actually a primitive type, a value 5, which would be an integer, but y, the value which y has, is a memory address. So what this visually means is y has a pointer to x. So whenever you use y, it is the same as pointing to x and then using the value inside. So this is how it works. This is what pointers are basically. And let's say you create another pointer of the same variable z, and this would also mean this. Let me call this. Okay. So z is also pointing to x because the value which z has is the address of x, which is a. Now what happens is, the problem with pointers is that raw pointers allow you to read the same thing and also write it, which can cause data races, which can cause pointers reading garbage values or deallocated values, right? So let's say we have two pointers y and z, but when we use the pointer y, we are changing the value of x to 6. This is causing inconsistency because you have two pointers, and while z is reading from x, your y is attempting to write into x, which would generally cause kind of a race condition. And that would be more prominent if both of the pointers are trying to write to the same value. And what could also be possible is that this variable, the memory, is deallocated. So this variable is deallocated, and your pointers, they don't point to the variable value, but they point to the address. But there's nothing in the address because this variable has been deallocated. So because of things like this, what Rust is attempting to do is it is trying to left shift your memory checks by checking the code and assuming how it would perform, how memory would be read, how memory would be written to. And at the compile time itself, it tries to restrict the developer into writing certain code and ensures that the code written is memory safe. So Rust has a lot of compile time checks, and it is very painful to get it to successfully compile when you're working in a project where time is of the essence. And this is the problem which I think many people face with Rust, is that the developer speed would be often very slow. But this video is about why was it done, the intent, which is to left shift memory leak checks into compile time, and also so that would ensure memory safety, and then to also avoid garbage collector pauses, which many languages have. So when a garbage collector would generally pause execution because you don't want to free memory which is being read, right? So everything gets paused, and then the GC deallocates memory, and then the process resumes. So that is the idea behind it. Now let's check how this would be in code. So I've created two variables x and y, and I've printed y. This is not an error, and this will not refuse to compile because they are inside the same scope, and every scope is defined by curly braces. So what Rust says that the compiler read this and it assumed that these variables are inside this scope only. But if you create another function, which can be my function, and you expect a some sort of a parameter which is of type 32, or maybe a reference to it. I'll go what this ampersand means, and you're doing something like this. So what this means is now your variables moved out of this scope into the scope of the function because it was passed into the function as a parameter. In that cases, it is very hard to see whether this variable is still being used or not. So what Rust does is whenever you create a variable and pass it onto a function, instead of passing a pointer, the default behavior is to pass the entire ownership of the variable to the function, which is called as the move. And let me show you how it works. Okay, before going into move, yeah, let's talk about oops and what should we do in the absence of oops. Okay, so what Rust has is it has types and it has behavior, which is called as traits. So how things work in Rust is that you can define something of a certain type, and the type can be custom, and then you define the behavior of that type when it is iterated on or with, and that would be called as a trait. So generally in OOPS you mix these two things. So you have attributes and you have methods. Methods define the behavior of the entity, and attributes are self-explanatory. In Rust you have structs, enums to define types, and then you have traits to define behavior for those types. So here x is an i32. This means a 32-bit integer, signed integer, sorry. And what this means is x has a certain type, and when you do certain things with x, it will have a certain behavior. So let me, instead of y equal to 6, let me do y equals to x. And now let's print both the values. Let's also remove. So like two variables and printing both of them. Let's run this. So cargo, and we specify cargo run to compile and run at the same time, but you can have individual commands for each step. For compile you would do build, and to run you just call the binary from the terminal. But here we are going to use run, and because this is a package, we would need to pass in p as a flag and then run this. So you can see it compiled and it also executed. So you must be wondering that we created x as 5 and then y as a pointer to x, similar to the diagram that we saw earlier. and let's make some changes to the value of x using y. Okay, so what I would do is I would change the value of y and increment it by 1. And this is our first error of the video, which is saying that cannot assign twice to immutable variable. So in Rust, a variable is either immutable or mutable, meaning that you either tell the compiler that our intention of this variable is to only read from it, like define once and read from it, or have the possibility that we might change its value sometime. So you need to explicitly pass your intention. Because we are changing the value, this variable is a mutable variable, and we do that using specifying mute. So let's run again. You can see that the output, let me clear it. The output is 5 and 6. We are printing x before and then y. So x is 5, y is 6. But what we did is we created a variable y as a pointer to x, and then we incremented y. So this, in the languages that you use, you might say this is a shallow copy, which should change the value inside y itself. X itself. But x does not change. Let me show you visual what happened here. So let's move this. So we define x first. Okay, let me copy the code here so that it is better to understand line by line what happened. So let's see what happened line by line. We defined x, and what that did is it allocated some memory in stack. By default, everything is in stack, and it had some address, let's say a. Now we created a mutable variable y, and we assigned x to y. What this did is it read your main thread sort of read the value of x, which is 5, allocated another memory b, and then copied the value. This memory is for y, I forgot to mention, and then copied the value of x as the value of y. And here, when we try to increment y, there is no pointer. Y got simply incremented and x was unaffected. This is what happened in these 3 lines. Create a variable, when it was assigned, the value of this was copied into another memory location, and then the memory was allocated for y according to the space of this x, obviously, and then it was given to y as its owned value. This is a behavior of all integer types in Rust. As I mentioned earlier, you have types and you have their behaviors. So this was an assign operation. So the behavior of any integer when it is assigned is copy. And what copy means is that whatever value the type has, copy it and pass it to the one wherever you have an assign operator. So in this case, x was being assigned. So behind the scenes, the value of x was copied and then given to y, and y had it as its own value. This was the simplest example of what a behavior is. So copy is an actual Rust trait, and you can create your own custom types and have them behave in a copy fashion. So for example, whenever they'll be accessed, the value would be copied instead of passing a pointer. So what if you did not want to copy, but you wanted to access it as a pointer? Now, there is a way to do it, but what Rust did is it abstracted the raw pointers into something called as reference. And the way you define a reference, let me go back to code. Uh, the way you define a reference is by ensuring that you have an n% before x. And this is erroring. I will not see what the error is because I know the error is that there's two. Before I describe the error, let me tell you that there are, just the way there are two types of variables, immutable and mutable, you also have two types of references, which is immutable and mutable. So when you reference x, you have to tell the compiler what is your intention with the value of x. If you're going to change it, then you should use a mutable reference. If you do not intend to, then you can use a shared reference, which is an immutable reference. And why is it called shared? I'll explain. So here we are trying to change the value. So we need to pass a mute and what is okay. So the type that we had defined is and mute. Okay. Type and mute. Okay. Let's just simply name this 6. Okay. Let's. So what happened here is we have y as a pointer or an immutable reference on stack, and that is the immutable reference of x. And what this is called in Rust is a borrow. So why is this called as borrow? Why give it a different name? Because generally you would have x as maybe an int, a pointer, I don't know the syntax exactly, but you have pointer to something, and here we are not giving the raw pointer to x, but a reference to x. And a reference is different than a raw pointer. It has an additional rule, and I will show you what the rule in practice using the code. So we have created a reference, but now to change anything inside it, we need to dereference it and then change its value. Cannot borrow x as mutable. Okay. So we have a reference which is a mutable reference to x, and we are, this star notation is to dereference the value that we took reference of. So now it's like you're going inside. So y is equals to a, and a is the memory address of x, but now you're going inside the memory address and getting the actual value, which is 5. So star of y is actually 5, and you're incrementing that by 1. So you're saying that I have a reference and I will dereference it to get the actual value, which you can see here, dereference from immutable reference to type integer, and then you incremented it by 1. Why is this erroring? Because unintentionally x is also getting changed, and we have not defined x as a mutable variable. If we do this, this error goes away. And here, what is the mutable? Okay. So for now I commented y. Let's see this code in practice. So now you can see that I printed x, and now its value actually has been incremented by 1, which is 6. Let me show how what happened behind the scenes visually. Let me keep this below and let me copy this. So what happened here is we created x5, okay, but this line we did a borrow on x. Remember this term borrow, because this is not a raw pointer. So what we did is we specified y is equals to a, and then you have a reference in this code, okay, and this actually went into the memory address, looked for the value, and then incremented it by 1. And this is what it looks like after this line, and when you print x, the value of x is 6. So this did not copy, which is the default, not a default, but they have explicitly maintained this behavior as default for all primitive types, which is the copy behavior or copy trait. So I will now use trait as a replacement to define behavior. Let's also drag this down. Now let me explain the rules of references and how it is different from raw pointers. Let's go back to code. So the rules of a reference is that you can either have a read-only reference which is also called as immutable, which is also called as shared reference, or you can have a write aloud reference, which is called as mutable, which is also called as exclusive. Why it is called as exclusive? Because you can either have multiple immutable references or one mutable reference at any given time in your code. That is why this is called as shared, because you can have multiple immutable. So 5 variables are sharing this reference, but you cannot have it at the same time as immutable reference, because you don't want to allow something to write or change a value which is being read by something else. Okay, so let me show you why this is not allowed. Let's do z is a reference of x, and you'll see the exact error. Okay, will this error? And no, this will not error, because we are not using it. Let me print this. So the compiler is also actually smart enough to tell whether this is being read or not. And let's do something here. Let's also do y. Now you'll see this will error, because you cannot borrow x as immutable because it is already borrowed as mutable. Immutable borrow. So this is an immutable borrow, and this is a mutable borrow, and both are being used inside the same scope, which is not allowed. Inside any given scope, you can either work on the mutable reference or the immutable reference, which is z. And if you comment out y, this might actually work. because you're not using it. So you saw that I don't need this actually. Can I print this before? Okay, now let's. So you see, even if I'm not printing anything, this said that cannot for as immutable, because down below, sorry, here it is. Okay, now this should yeah. So before we mutate it, the value is 5. After we mutate it, the value is 6. We are printing the same variable, right? So the point is that at any given scope, you can either do something with the mutable reference, or either have multiple shared references. And what I did earlier would error if uh, you are doing something with both types of references uh, simultaneously. Okay. And this is the error in practice. And this is the way that you might access something in memory in stack and as mutable or immutable. Now let me show you by defining a type myself, uh, and then try to sort of implement the copy behavior, because this is integer, and whenever you use something with integer, it is auto copied. Let's create our own type. So I will define struct node, and then the inner is actually 932. Now let's define x and node, and then let's define y as x, and let's print x. This has an error. Before explaining the error, uh, because you saw earlier that uh, let me go into the okay. So let me explain that. So the error is node does not implement display. Okay. Or you can just do x dot. So you can see the error is borrowed of moved value x, value borrowed here after move. That means that judging that this here, what we did earlier to let y equals to x, this is the same syntax, but here x was equals to 5 and now x is equals to node. But because node does not have a copy behavior by default, accessing x after it has been assigned to y is not allowed. Let me show what happened visually. So let me also copy the code. So when we define x as a node. Here instead of x being 5, x is actually n of 5, and so when we created y equals to x, what happened is the value inside x was moved out of x, assigned to y, and then y was created and x was dropped out of memory. This might also be or here, doesn't matter for explaining. So x have been dropped out of memory, I think. Yeah. So the point what I'm trying to make here is this is what happened line by line. But here we try to access x dot inner, but x does not exist anymore. That's why this is the error that you see. Now let me show you in code how to prevent this error and get the initial output of 5 and 6 which we had with x and y. So you want this thing to copy the entire thing whenever it is assigned. So what you do is, the fastest way to do is define that this node has a behavior of copy, and this is the fastest syntax to do that. And you have clone. So now you see that this error goes away, and if I run this again, you'll see you had 5. Let's do something with y dot inner plus this work. No, because it's not mutable. And you can no. You can see we have 5 and 6 again. So what I did is I created a type and had it specifically define an additional behavior that I want it to have, and that behavior is copy and clone. But this has been already defined by the developers of Rust, so we don't have to implement the behavior ourselves. But you can also define custom behaviors and implement it on your own. That would be creating a trait and then implementing it for any type of struct. And this is how you can sort of accomplish things in an oops manner, because oops does not exist by default. So you would have a struct and then you would have behaviors of the struct, and that would be traits. So this node has the behavior copy and clone, which means whenever it is assigned, the values will be copied. So you can visualize how it would work by from first example of copying x equals to 5 and then giving 5 to y, and then when we change y, x is not changed because y has its own memory. The value of y is not an address but an entire but the value itself. So this is basically how you like write code in Rust, by defining structs and then custom behaviors. Now what am I missing? Okay, so let me tell you why exactly is the multiple references to something is an issue. Okay, let me open the visual. Let's say you have, let's make it x here again. Then you have y pointing to a, and then similarly you have another. I'll keep the name as y to make it faster. So everything is a pointer to x, but let's say one of this is actually a mutable one, which maybe can change the value of x, and the other ones are immutable, so they don't change anything. But the problem this would cause is that when you're trying uh, to create this scenario, you will have multiple shared references and a exclusive reference or a mutable reference at the same time, which is like you would perform operations on it at the same time, is what I mean, which is not allowed by default in Rust, as we saw when I did print xyz, because that we are accessing it, that's some sort of operation. It was not allowed, but you still want this behavior. How can we do that? I want to have multiple readers and one writer and do operations on them at the same time. There is a way to implement this, and the way to implement that would be, so now we are going from memory to references, and before that let me tell you what a borrow is. So borrow is additional rules, and those rules would be uh, about shared refs and exclusive refs, and you cannot operate on both at the same time because that would cause data races or something. Let me show a visual example. Imagine that this is a vector or an array of items, a list of items, and you have multiple references to this vector. But let's say you're reading this vector, but while reading this, you added another value to this vector. So when you reach here, you see this is not the last element, so the loop goes on, and at every step, you add another value, and you add another value. So this is infinite iteration, which is one case of letting write references and read references, letting them exist at the same time. This is one sort of error which could appear, and this error would be a runtime error. So Rust has all made all these rules at compile time because it is the job of the developer to not let this happen, but it can happen. So what Rust has tried to do is collect all the cases where data races and memory invalidations might occur at runtime and prevent them at compile time by defining the rules that you can operate on multiple read references or a mutable reference within a single scope. Okay, and the enforcement of the sharing is called as a borrow. In simple terms, this would mean that y borrowed the value of x, and the way y is using it, that it might change it or it might not. Then z borrowed the value of x, and z will not change it, so z is an immutable reference. But the moment I print both of those at this, like line by line, it errors because again I'm using the same terminologies, but it is to put pressure on the most fundamental rule of references, and that behaves as a contract, and you can say that the name of the contract is borrow, similar to something. You can also think of references as wrappers over raw pointers. So I have a raw pointer, but I have wrapped it around my own logic, and inside that logic I'll see if the value already has a read reference and it has a write reference, then the compiler will try to see if both of those are working. If not, then if they're accessed, then it will error. So this rule is called, or this behavior is called borrowing and referencing. And what invalidates this is called the borrow checker interest. So it checks how it is borrowed, mutably, immutably. So let's go back to creating this, where you have multiple read references and one write reference. So logically, having multiple readers and one writer is not a problem, because not two different entities are not writing to the same thing. By the way, also let me show you what would happen if we have two mutable references at the same time. So let me use this as a mutable reference, and then this should also be mute. And then let me create another mutable reference. And this is the error is cannot borrow X as mutable more than once at a time. This is the reason that this is an exclusive reference, because you cannot have two writers at the same time. You can have either one writer or multiple readers. But yeah, so the value of X is borrowed. So imagine borrow as you had an apple and I borrowed it. Now somebody else comes to you seeking for an apple, but you don't have it because it is inside the shared reference, but I am currently accessing it, and I might I might eat it, I might leave it as it is. So that would cause problems for the one who came to you seeking the apple. And let's remove X from here. And then let's try to so can we bypass this? This is currently not allowed, but we want to have mutable and immutable exist and be printed at the same time. Let's first visualize our logic. So X is a node of 5. Similar to how references wrap over raw pointers, we can wrap this node itself over another using another struct and then define the behavior there. What do I mean is, we have seen how copy works. So to allow this to happen, what if whenever there's a shared read reference, we don't give the address, but we copy the value. So this would be so you get the point. And only one thing, which is your writer, will have the actual reference. As seen that this has a memory address and the others has values. So you have multiple readers which have values which can be implemented through copy. And then you have one writer, which is actually a mutable reference. So this is not being done currently. So what we can do is we can create our custom wrapper over N, and then we could reference C directly. We could have a way to get the value inside of C. I'll show how. And then whenever this is accessed, this should be copied and pasted. and paste it again and paste it again for multiple types of readers. And the pointer to this would be given only to the true writer. So this is what we want to implement. And this in Rust is called as a smart pointer because it is smart. And this is an additional behavior over the default reference. So let's do this in code. So what I'll do is I'll define another struct which let's name this sharing, and the inner value of this, it's not necessary to name this inner, it can be anything. Let's name this node, and this would be a node or of type node. So I created a wrapper over node, and what I simply, so currently if I access this shareable, it will behave the same way because there's no additional behavior. We just created a wrapper, but the wrapper needs to have behavior. So I will implement something for this struct, and the way I will do it is impl, which is short for implement, and I will specify. So let's create a constructor first, and whenever you have a node of type node, simply create or return a self, and inside the self you will have node of type. So I created a constructor which allows us to create shareable structs in a more elegant manner rather than the direct constructing of the struct. And because the name of these is same, I can actually do this as well. And then I will define a way of what happens when this value is read by doing get, and I will specify what would happen if this value is read by defining set. So first let's go to set. So when you're going to set something, you'll have a reference to your self, and you will have a node of type node. So what you want to do is you want to set the type of self.node to actually node. This is not allowed, which you can see that this should be a mutable reference. And then let's get to get. So for get we do not change anything, so it could be simple a shared reference to self, and we simply return the node. And pay attention here that the thing that we are returning is a node and not a reference to the node. And would this move the value outside and then be passed to the variable assigning it? No. Why? Because we have implemented the copy trait. And this would kind of this is kind of a wrapper using which you can you can create a wrapper which behaves the way we want. Multiple writers own and only one reader. So let's create this. So instead of this code, I will copy this over and comment this out. So we created X as a node. Let's define our first node as shareable new X. And what happened here is I will explain visually later, but let's code. So let's do Y, or let's just change definition. So now Y, instead of doing and mute, we can define Y is X dot get, because X has this behavior. No method named get from node. Okay, so we have to do in1.get, and then Z is actually, we would want to create another node. Let mu b. So the inner for this is 6. So we would want to set the value inside to actually be. So because we are here, we defined that the first parameter of this set is a borrow of self in a mutable fashion. That means the variable itself, which has the value of shareable, should be mutable. Let's see. Now let's print this. And do you have Z? Okay. So n1 dot node, or you can say n1 dot get dot node. And we would like to call this after I get and after I set. So you can see there are no errors here, and let's run this. You can see the first was 5 and the rest was 6, and what we did is we had a way to create something and then have it change and then fetch the value at the same time. So instead of n1.get, we could also do we could also define let w is equals to n1.get here, and then instead of n1 we can do w, and here we can do y, and you'll see that this still does not error. So this was not necessary. Okay. So you can see that this still works, and we have 5 and 6, and we're allowed to have readers and writers at the same time. So this is kind of a getter setter functionality which you see in OOPS. And what we did is we wrapped our value by another, we wrapped our struct by another struct, and we defined whenever we find a way to access the value inside it for someone, and whenever it is accessed, we want it to be given in a fashion of copy. And we can also let someone change the value inside it. So currently we are changing the entire node But what if we only want to change the value? So for that, uh, we have to define this, uh, because what we want to uh, sort of give away is not exactly node, but the value inside it. Currently, the inner of node is an I32. So I will not go into generics now, but instead of giving the entire node, we only want to give the value. How we can do that is we can do self.node.inner, and here is we want to we have a number 32, and we want to do self.node.inner equals to n. So this is for changing the values rather than the node. So we don't need this extra node. And then we created a shareable node from X. And what Y will get here is I32. Earlier it was node. Now it is I32. So we don't need to do either places. Now let's set n1 to 6. Then get it again. And this would be, so you can see we ensured the functionality that we had by default with integers with a custom type, and that is by allowing readers and writers exist at the same time and doing operations on it, and uh, basically uh, bypass the rules of shared references and exclusive references and create a custom wrapper and define things on our own. So you see how to replace sort of oops here. These would be methods in oops scenario, and then your attributes would be defined somewhere here, like self dot v, but this is not allowed in Rust. So what we created is we created a wrapper and we made it behave the way we wanted to behave. And so this is how things are accomplished in Rust in the absence of oops. Can we create a uh, so this is working because I have defined n as mutable. But what if I don't define n as mutable? Then we are not allowed to do set here, and because this would fail, and that error would go away if I remove this. But then we cannot change the value because uh, we have a shared reference. So the error here went away, but the error here did not go. So what we can do is, instead of having a node, we can use an unsafe cell and I think I need to import this. So the way you would import anything in Rust is by use statement, and is it inside ops? Is it inside cell? Yes. And what this means is now you have to do node is wrapped over unsafe cell. So you have two layers of wrappers instead of one. And this here, uh, no field type inner on unsafe cell. Okay. So when we mention self.node, this is the unsafe cell. So we want to go inside unsafe cell, and we can do that by dereferencing our unsafe cell, and then maybe do get, or can I do simple get this match type? So you can see that this is an unsafe cell, but when I do get here, this is a raw pointer. You can see this is not n% mute node, this is star mute node. That means that this is a raw pointer. That's what unsafe cell means. It is used to work with raw pointers rather than references. So this is a reference, but we want to use a raw pointer. So we convert the reference into a raw pointer, and then we get the value inside it. And that's basically how we sort of bypass the rules of references, is by we dereference them, or we use them as raw pointers. And raw pointers allow you to read and write at the same time. So you have this, then okay. So I dereferenced it, and instead of the pointer, it gave me node. So I think I'll have to just do here. Enough. But you can see it's still error saying that dereference of raw pointers is unsafe, because working with raw pointers is not safe. That's why we have references. So we need to mark this as unsafe, because the compiler will not allow it. But you can tell the compiler, I know it is unsafe. That's what this means. So anything which inside the braces of unsafe, I know it is unsafe, but I've ensured that this will not error at runtime. So the compiler allows it. And similar to here, we want to change here, but this gives you the unsafe cell, and then you can set anything inside the unsafe cell. But currently, what we can do is we can do get first, same way, and then get will get you the raw pointer. Let's dereference the raw pointer, and then we have node. Okay, and node also has its own behavior for set. Or node doesn't have. Never mind. So we can do is inner equals to n. And you can see this is also unsafe. And you can see there. Now you can have writers to this without having a mutable reference. Let's do this. It's also not necessary. There's no mutable reference currently, but hopefully this should work. And you can see it prints 5 and 6 for y and z. And we could also do this. We could also do this here. And you can see that this will not error. So we wrote some code which was erroring earlier by implementing our own behavior and setting explicit methods on the struct shareable, which defines how it would behave. So whenever you do get, it would copy the value inside the node and return the inner. And whenever you want to change something, it will again give you a. It would again change the value. So this is basically how you would you can create your own values. You can create your own rules. You can create your own smart pointers. Sort of. This is not exactly a smart pointer, but this is a smart wrapper for us to do something which is not allowed earlier. And what this did is, let me show you now more visually. So at first I created n5, but then we wrote n1 is, let me see if I can paste the code. Okay. So I'm pasting the code, and then this code. So what happens is I defined x equals to 5, and it had some memory. Then I created another variable n1, and now this is a wrapper over x. So this is the wrapper, and the value of n5 is moved sort of here. And then this is dropped, and n1 sits here. You can is x actually dropped? Okay, so I think x is not dropped. Let me go back to the code. I just noticed something. So x is not dropped, and it is still accessible, and we can get the value, the original value, which is 5, because whenever it is passed to shareable, because it implements copy trait, the value of n5 was copied and given to s. That's why it was not moved. But if we want to ensure that this should be moved, then we simply remove this, and you can see now this errors because it has been moved. And if I remove this, this is not error anymore, and you have 5 6 without node implementing the copy trait. So now let's go back to the diagram. So this is what happened, and then when you did let y equals to n1 dot get, then it went inside the value and got to n5, and then it went again inside n5 and got you the value 5, and then it copied 5 and it copied 5, and then it gave it to y, and then y has its own memory. Now you have you changed something, I think. So whenever you change something, it will go inside and change this value to, let's say, 6. So whenever you do this n1 dot set, it changes it to 6, but now y does not change. But when you do w again, now w will iterate over the new value, and therefore w is 6. and then you printed both, and then you got 5 and 6. So I think this was too much for one session, but still I would like to stop here for this session and just let you know that how what references are, how they behave, what are the rules, what cannot be done, and how to create our own types to bypass those rules and define our own behavior. And I will create another session which goes over the smart pointers, because Rust does not deal in raw pointers. You can, but there's the default way is the reference instead of the pointer. Uh, that's the way the developers of Rust want you to work. But you can bypass some of the rules and then tell the compiler to avoid checking certain code because it will fail according to the compiler. But you will make sure that this is not happen. And that was all which was covered in this session. And I'll see you in the next one. Thank you.